Alright, in this video here we're going to talk about piecewise defined functions, and we're going to look at an example of like evaluating and then also graphing a piecewise defined function. Alright, so first, what a piecewise defined function is, it's a function that's defined by different formulas on different parts of its domain. Right, so when x is these certain values, the definition is this. When x is these other values, it's this other definition, right? So there could be two or more pieces. Some piecewise defined functions have 3, 4, 5 pieces to it. Most of the ones you see have 2 pieces, but you could have more than 2, right? So different formulas on different parts of the domain for that. So the different formulas apply to different x values. And when you graph a piecewise defined function, that graph consists of separate pieces, right? So there will be, it's almost like you have 2 different graphs put together on one single coordinate plane, and that's the graph of a piecewise defined function. All right, so we're going to look at an example where we graph a piecewise defined function here. Right, so we're asked to graph the function f of x equals, and then notice we have that brace thing there. That's our clue that what we have is a piecewise defined function, because there's 2 definitions here. There's x squared and 2x plus 1. Right, so the function doesn't equal both of those things at the same time. Right, f of x is equal to x squared if x is less than or equal to 1. Right, so if my input values are less than or equal to 1, I use the function definition f of x equals x squared. Right, f of x equals 2x plus 1 if x is greater than 1. Right, so if my input value is bigger than 1, then I use the function definition f of x equals 2x plus 1. Right, so I never use both of those definitions at the same time. Just depending on what my x value is, and you look at these inequalities here, whether it's less than or equal to 1 or whether it's greater than 1, that determines which piece of the function I use and which one of those definitions I use to evaluate the function and also to draw the graph of the function. All right, so that is our function that we have to graph. So in order to graph this, I'm going to set up a table of values. Right, we call this graphing method the point plotting method, where I figure out a bunch of points and I plot those points on the graph, and then I just kind of connect the dots. Right, so let's do, I put on the graph up here, my first value was -2. So let's start there with our first x value of -2, and then we'll do -1, 0, 1, 2, 3, and I guess we'll stop there because we kind of ran out of space. So for x equals -2, well, I need to figure out my y coordinate, which comes from f of -2. Right, remember, if you didn't look at the video that I did about the graph of a function and what the graph of a function is, the graph of a function is the set of all points x comma y, where x is my input value and y is the output that corresponds to that input value. So to find the y coordinate when x is equal to -2, I plug -2 in my function, and then I do the calculation, and whatever number I get, that's my y coordinate for that point. Right, so I need to find f of -2. All right, so what's f of -2? Well, I have a piecewise defined function, so before I can say what f of -2 is, I have to figure out which one of these 2 definitions do I use, and again, it comes down to the inequalities. All right, if x is less than or equal to 1, or if x is greater than 1. Well, -2 is less than 1. All right, -2 is a smaller number than 1, therefore, I'm going to use that first definition, f of x equals x squared. All right, and x squared, if I do -2 squared, that's going to equal 4. So when x equals -2, y equals 4, that's a point that I can put on my graph. Right, so the x value is your input, plug that into the function, whichever one of these 2 pieces it belongs to, whatever the output is, that gives you the y coordinate when x equals -2. Then I go to my next number, -1. Well, once again, I have to decide which of the definitions I need to use. -1 is also less than 1, and so once again, I'm using that x squared definition. So f of -1 is going to be -1 squared, which equals +1. So there's my point, -1 comma 1. All right. Then I move to my next point, x equals 0. Well, once again, 0 is less than or equal to 1, so I'm still using this first definition here, x squared, right? And 0 squared equals 0. So there's my point, 0, 0. Then I move to x equals 1. And this is the one where sometimes people get hung up on it, right? X equals 1, well, both of these definitions involve an x and a 1, so which one do I use? It's the one where x is equal to 1. Right? The second one down here just says when x is greater than 1. The one up the top says x is less than or equal to 1. Right? Since this one has the less than or equal to, I'm still using this first definition. Right? F of 1 equals 1 squared, which will be 1. Right? Again, Since this is less than or equal to, that's the one I use when x is equal to 1. So it's still the x squared definition, and 1 squared equals 1. All right, so that's where that first part of the function is going to stop. So let me kind of draw that graph there. And if you know anything about the graph of a quadratic function, y equals x squared, this is the graph of y equals x squared, but it stops at x equals 1 because my definition is f of x equals x squared. Only when I get to x equals 1, when x is greater than 1, I have a different definition, so I'm going to have a different graph. All right, so let me move on to my next number now. X equals 2. All right, so now I need to find f of 2. Well, which of the definitions do I use here? In this case, my x value 2 is greater than 1, right? 2 is a bigger number than 1, so now I'm using the second definition. It's going to be 2 times 2 plus 1, which is 4 plus 1, which equals 5. So f of 2 is going to equal 5. So there's that point up there, right? If I go to my next number, 3, f of 3, well, once again, 3 is greater than 1, so 2 times 3 is 6, 6 plus 1 is 7. So f of 3 is going to equal 7, which I'll put that point up in here somewhere. It's kind of in the way of my definition, but that's about where that would be, right? So, and again, if you know what the graphs of different types of functions look like, the graph of x squared is a parabola, right? It's a curve. The graph of 2x plus 1, 2x plus 1 is a linear function. That graph is going to be a straight line. Right now, the straight line for 2x plus 1 is going to go through here and go upwards that way, like that, but it doesn't start at x equals 2, right? This is the definition, 2x plus 1, if x is greater than 1. 2 is not the first number that's greater than 1. Right? What about 1.5 or 1.2 or 1.1 or 1.01 or 1.00001, right? This line has to go all the way to the first number that's just barely bigger than 1. All right, so in order to figure out where that's going to go, I have to do one more thing here. I have to figure out, well, I know this definition here, the second definition, the 2x plus 1, that's not the definition when x equals 1, but what if it was? Right? What if I did 2 times 1 plus 1? Well, that would give me 2 plus 1, which is 3. So when x equals 1, y equals 3, it's almost like that's a ghost point here. Right? It's not an actual point on the graph, because this function is not defined here when x equals 1. It's defined down here when x equals 1. Right? Because when x equals 1, I'm using the x squared definition. But, like I said, this graph, or this function, doesn't skip from 1 to 2. It still covers all the numbers in between 1 and 2, which means I need to bring this side of the graph all the way down to x equals 1, just not including x equals 1. Right? So I put an open circle at the point 1, 3, right? And just if I label some more of these points here, right? So I put an open circle at 1, 3 to show that the function, is not defined there, right? The closed circle down here at 1, 1, that's where the function is defined when x equals 1. But as soon as I move past 1, as soon as I go to 1.00001, the graph jumps up here, right? And then from there, it continues along the graph of 2x plus 1, that straight line that goes through the points 2, 5, and 3, 7, and so on. Right? So that's what the graph of a piecewise defined function generally looks like. It's like you're graphing two completely different functions here, the x squared and the 2x plus 1, but they're going to stop. Like, it's almost like if you were to graph both of those functions on your coordinate plane at the same time, and then wherever that definition, the definition changes, in this case at x equals 1, it's like you just kind of slice right through and just cut off the parts of each graph. Right? At x equals 1, the left side of that straight line disappears and the right side of that parabola disappears, and you get the graph that we have here. All right, so that's how you can graph a piecewise defined function, by plotting points, just paying attention to your input values and where it falls in terms of these inequalities over here, and then using the proper function definition depending on your x value, and then just making sure you stop at the correct point. Right now, for piecewise defined functions, a couple common mistakes I see people make on these, and people make these mistakes all the time, so pay attention to this, because you might be about to make this mistake, and I would rather you didn't make it. For a piecewise defined function, the two pieces do not have to connect. Right, so this one stops at 1, 1, and then it goes up here to 1, 3. You don't draw a straight line connecting those two. it doesn't exist, right? It stops at the point 1, 1, it skips up here to 1, 3, and then goes from there. Or sometimes people don't do this point, but they have the 1, 1 and the 2, 5, and they somehow try to connect those 2 points and then have it continue on from there. They don't have to be connected, right? Sometimes a piecewise defined function, the 2 pieces of the graph do connect. Like if this line was a little bit lower and that empty circle happened to land right on top of this filled in circle down here at 1, 1, well, then the 2 parts of the graph would be connected, right? So it is possible for that to happen, but it's not necessary for that to happen, right? So if you graph the 2 parts of the function and they're not connected, don't try to fudge it and like connect them somehow. They're just not connected, and that's okay, right? The other major mistake that people make on these types of problems, and I already mentioned it, is just kind of doing this point at 1, 1 and then doing this point at 2, 5 and going from there and completely leaving off all those numbers in between 1 and 2. Right? Remember that there's more numbers here than just the integers, just 1, 2, 3, 4, 5. Right? There's all those decimals and fractions in between, and your graph has to cover all those numbers as well. Right? So when you're graphing a piecewise defined function, whatever this is where this definition changes, you really have to plug in that x equals 1 number into both of those definitions. It's just that one of those is going to get a filled in circle and the other one is going to get an open circle. The filled in circle goes wherever the one for x equals 1. The open circle is the one that doesn't have that equal to sign on it. All right, so I hope that makes sense as far as what a graph of a piecewise defined function is supposed to look like. And if you're ever not sure, just start plotting points and figuring out the x and y coordinates. Just make sure when you plug the x values in, you are using the correct definition for the function, the top one or the bottom one, depending on what the x value is. All right, so that's what the graph of a piecewise defined function looks like. One more quick topic while we're looking at this graph. A continuous function, right? Continuity is something that's important with functions, especially when you get into calculus. There are certain things you can do in calculus when you have a continuous function that don't work when your function is not continuous. So it's an important thing to understand and to know what it means. And it's a pretty simple definition. If you get it, it's pretty easy to tell whether or not a function is continuous. But a function is continuous if the graph has no holes or breaks, right? A hole would be something like this. If I just real quick, like just an empty point in the middle there where the function is not defined. A break would be something like what we have here, where the function is going along, the graph is going along, it gets to this point, and then it breaks and like jumps over to this other point before it continues. Right? So this piecewise defined function that we graphed up here is not continuous. Right? Kind of the kindergarten definition of a continuous function is you can draw the entire graph without lifting your pencil off the paper. Well, I cannot draw this graph, I can draw this part, but then I have to lift up my marker to go up here to draw the rest of it. As soon as you have to lift your pencil off the paper, it's no longer a continuous function, right? And if you know what the word continuous means just in everyday language, it kind of makes sense, right? Continuous basically means each point is connected to the next point. Well, here at x equals 1, that's not connected to the next point up here, and so it's not a continuous function, all right? And a lot of piecewise defined functions are not continuous, but they could be. Like I said before, if this line was moved down a little bit more so that empty circle was right on top of the filled-in circle, then it would still be a continuous graph. Right? So it is possible for a piecewise defined function to be continuous, but not always, and most of the time it's not. All right, so that's a little bit about piecewise defined functions.